guys, this is the Academic Chemistry Chapter 8, Section 2, Covalent Bonding Part 2. And today we're going to go over the steps on how to draw a Lewis structure. So what do you need to know, what do you need to do, and how to do it. All right, so the first Lewis structure we're going to draw is phosphorus trichloride. Now there are some simple steps that if you follow them every time, you're going to get the right structure. So just follow along the steps. We'll do one example as we go along, and here we go. So the first step is determine the number of valence electrons from each atom in the compound. And you multiply that by how many atoms and then add up. So basically in phosphorus trichloride, you've got a phosphorus atom and you've got 3 chlorines. Now each of those atoms, so all 4 of those, the 1 phosphorus and the 3 chlorines, they each bring their own valence electrons to this bonding party, right? So phosphorus, if you find it on your periodic table, which you should have out, if you don't have your periodic table, go ahead and pause and grab a periodic table. So phosphorus has 5 valence electrons. And I've color-coded this so it makes a little sense here. So phosphorus brings 5 valence electrons to phosphorus trichloride. And chlorine has 7 valence electrons, but there are 3 chlorines, so we need to multiply 7 by 3. Then you add this up. So 7 times 3 is 21, plus 5 is 26. So in phosphorus trichloride, there are 26 total electrons that we're working with. Next, you're going to write the symbols of the atoms in the compound. The element with the fewest atoms is usually the center. Now, sometimes you might have like a 2 and 2, or something you say, well, which one goes in the center, which one goes on the outside? Keep in mind things like chlorine or any halogen. So any halogen and any hydrogen, they only make 1 bond. So they always stick on the outside because they can't link different atoms together. So even if you didn't know that there's only 1 phosphorus, because the other element is chlorine, which is a halogen, halogens always go on the outside. So I think of it like the number of bonds an atom can make is like how many arms they have to link onto other things. Since chlorine can only make 1 bond, it only has 1 arm, so it can always only go on the outside of a molecule. It can just hold on by one side. It can't grab onto multiple things. Okay, so I'm going to put phosphorus in the middle, and then I'm going to put my 3 chlorines outside of it. The next step, step 3, is you're going to draw the valence electrons. You're going to draw them in pairs, and you're going to go around the outer atoms first, and you're going to fully fill their octets. Now remember, we have 26 electrons we're working with. So chlorine gets 8, 2, 4, 6, 8. And these 2 here are those bonding electrons between the phosphorus and the chlorine. And then my next set, so I've done 8, then 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I've given out 24 electrons. I had 26 total to work with. Any extra electrons are drawn on the central atoms. The central atom is this guy right here, phosphorus. So I had 2 more, because if you remember, I gave out 24 electrons to my chlorines. I have 2 more, 26. And if I look at this right now, everyone's octet is satisfied. You draw a little circle around every single atom, you're going to find 8 electrons each. So this is happy. This is it. If it wasn't happy, and we're going to do some examples of this, then you would have to move around electrons from the outer atoms and bring them into sharing to the central atom to make double or maybe triple bonds so that everybody has a satisfied octet. At the end, you really want to redraw your molecule so that those bonded pairs between turn into straight lines. And that makes it a lot easier for your eye to pick up what's a bond, what's a lone pair. And especially when you get into a lot more complicated structures, you're going to really appreciate that you have those straight lines to tell you where there's a bond versus dots where there are lone pairs. So let's do another example. All right, so we've got carbon disulfide. So I'm going to go ahead and color code it again. Carbon brings 4 valence electrons to the party. Sulfur brings 6. I have 2 sulfurs. I add them up. 6 times 2 is 12, plus 4, 16. So I have 16 electrons to work with. I've got carbon and I've got sulfur. Carbon, there's only 1. Sulfur, there's 2. So I'm going to put carbon in the center and sulfur on either side. The rule is satisfy the outer electrons octet first. 2, 4, 6, 8, 10, 12, 14, 16. And that's all the electrons we have to give out. So let's check and see if everybody's octet is satisfied. So first I want you to look at sulfurs. the sulfur on the left. So if I draw a circle around it, it looks pretty happy. Let's look at the other one. Sulfur looks pretty good. What about carbon? If you draw a circle around carbon, there's only 4 electrons. So carbon is not happy right now. It is deficient by 4 electrons because it only has 4, which means it needs to share 4 more. And luckily, each sulfur's got plenty of lone pairs, and you're going to pull from the lone pairs. So this lone pair is going to move over there, and this lone pair will move over here, and there you go. There's your structure. Again, draw it a little nicer. So you want to draw it with the lines. Notice you now have a double bond between each. The other thing you want to keep in mind is electron pairs repel other electron pairs, which repel bonds and all that. So these lone pairs, I'm going to draw as far apart from each other and as far apart from these bonded pairs as possible. That's why they're not the north, south, east, west that I've talked about before. It's kind of all spread out as much as possible. Notice the electrons are still stuck with their pair, but their orbital kind of pushes away from everything. Okay, couple things to watch out for. Carbon doesn't like having lone pairs of electrons. It's not going to happen in a neutral covalent molecule. Carbon's always going to have 4 bonds, no lone pairs. It's different if you have like cyanide is a polyatomic ion, then it does have a lone pair, but if there is no charge on your molecule, then carbon does not ever carry lone pairs. So watch out for that. Oxygen tends to have 2 bonds and 2 lone pairs of electrons. And nitrogen tends to have 3 bonds and 1 lone pair of electrons. Obviously, some of this stuff changes from time to time, but that's the general rule that you want to do. And keep in mind, atoms of elements in similar groups are going to have similar properties. So like sulfur is in the same group as oxygen. So sulfur will probably also have 2 bonds and 2 lone pairs because it acts a lot like oxygen does. Okay, best of luck with your Lewis dot structures, and I'll see you in the next set of notes.